Good morning, good afternoon, and good evening. Hope that you are all doing well and staying safe. Here is Mariam Shref, a senior petroleum engineering student at the Lebanese American University. Welcome to the third and last lecture of our course, Application of AI in Petroleum Engineering, presented by a special guest speaker, Dr. Ahmed Farid Ibrahim. For those who have missed previous lectures, they may visit Arab Guru's YouTube channel. All sessions have been recorded and uploaded on YouTube. So let me reintroduce Dr. Ibrahim. Dr. Ibrahim is an assistant professor at the Department of Petroleum Engineering at King Fahd University of Petroleum and Minerals since January 2021. He worked as a teaching assistant at the Department of Petroleum Engineering at Cairo University for 3 years. Moreover, he has more than 10 years of diversified international experience, including working for Advantech International Company as a geomechanical engineer and Apache's North America Unconventional Resources region as a senior reservoir engineer. Dr. Ibrahim earned his PhD in December 2017 from Texas A&M University. Finally, his research interests include reservoir modeling and simulation for conventional and unconventional reservoirs, production and well performance analysis, shale gas and oil resource assessment and characterization, and CO2 sequestration, and finally, AI application and reservoir engineering. So welcome, Dr. Ibrahim, and thank you for your collaboration. Now, as a reminder, if you have any question related to the technical content of the presentation, please feel free to drop it down in the Q&A section. Without any further ado, Dr. Ibrahim, the mic is yours.
Assalamu alaikum, everyone. Thank you, Mariam, for the introduction. Good morning, good afternoon, everyone. Thank you again for attending my presentation here today. So for this webinar, we had we had two sessions before. The first one, we introduced the data analysis for machine learning application. And this data analysis, we said it is a univariate problem or a multivariate problem. For the univariate problem, what I want to know the distribution, I want to know the location, the scale of the each property. And for the multivariate property or problem, I want to know what is the relationship between the input parameter with the output parameter and the relationship between the input parameter and with each other. For the second session, we discussed how to evaluate the model, and this including the cross plot, the trend for the curve to see how the actual versus the predicted values match, and with some equations for the R-square, correlation coefficient, absolute error, or RMSE, which is the root mean square error. This is all of it for the regression, and we saw that the confusion matrix can be used to evaluate the classification problem. For today, inshallah, I'm gonna go through some of the application of the AI in petroleum engineering. I'll give some examples, case studies for different petroleum engineering, like production, well logging, or drilling. And I may touch the reservoir engineering concept, AI concept in reservoir engineering. So let's start with the first example, which example of AI or machine learning in production engineering. So for today example, I'm gonna use AI to predict the oil rate from the choke parameter. So as you know, the oil rate per each well. So usually in oil reservoirs, we have many wells, okay, and all these wells here are connected together to the main line and from it to the processing system. Knowing the flow rate for each well is very important in order to evaluate the well performance, to know how this well here is doing. It's important for the history matching, rate transient analysis, build-up analysis, and so on. So it is very important to do to know or to allocate the production for each well. There is many techniques that can be used to do that. The first one is the test separators. So test separator, it is like a small separator that can be used, and it's portable. You can move it to the location, do your test, and take it back. Or from time to time, you have like many wells. What you do is just to connect one well to the separator and close the other, and then do the well test for this one here to know what is the test, what is the actual production for this one here. And then you use this percent. So now, for example, for this 3 wells here, you are producing like 1,000 stock tank barrel, for example, and whatever 1,000 standard cubic feet. So you use, when you do the separator test, you know the ratio of this one here comparing to the total. So this one here is producing 500 stock tank barrels. That means this one here is producing half of this one here. So you use this half factor as allocation factor for all for the next period, for example. So you do this test here every month, every 3 months, and so on. The second technique, the second way of doing that is having a flow meters. In the wellhead here, you can put a flow meters here, multi-phase flow meters that can measure the or estimate the flow rate for each phase, oil, gas, or water, based on the phase, the properties of each phase. The problem with this technique here, as you can see here, the size of this equipment is too big. Sometimes it's too difficult to put it in the location, like if you have your platform. The separator here also sometimes it's difficult to move it from a place to another or to install it in the location. Plus, this tools here is very expensive. Separator here, you don't have a continuous measurement for the flow rate. It is just from time to time, and then you use it to make the allocation. So this one here is not that efficient way to measure the flow rate per each well. Instead, there is some correlations that is based on the choke in order to measure or estimate the actual flow rate. So for each well, it has a certain choke, and this choke here is basically control the fluid flow from the well in order to like adjust the drawdown, avoid any sand moving or sand production. So each well has this choke. So for this choke here, you can measure some parameter from it, like the pressure here, upstream pressure, the downstream pressure. And later on, when the fluid goes to the separator, you can easily know the gas-oil ratio. And this choke here is controlled by like a certain size, which we call it the choke size. So there is many empirical correlations that have been used to estimate the production, which is basically here, as a function of the upstream pressure, gas-liquid ratio, the choke size. And this one here, it is localized. It is different based on the data sets that were used to make the fitting for this equation. In order to estimate this constant here, we have the C, M, and N. So this one here is good. It's a good option to calculate or to estimate the oil rate or the liquid rate from the for each well. But the problem is it is localized. Like it depends on the data that we are used, and each time you need to do this regression in order to reach or to use it for the next prediction. Second, for the most of this one here was done for low gas oil ratio system. It's not for good or high gas oil ratio. So if your gas oil ratio is higher than 1,000 standard cubic feet per stock tank barrel, sometimes this one here fail and give you a very big error. So this was our the problem statement why we can introduce AI for the application of measuring the oil rate from the choke parameters. The first thing is to know what is the flow chart that we're gonna follow in order to do that. Firstly, we're gonna start collecting the data. Okay, we see what data we have, and then do some data processing, which is similar to what we show in the first session, and then start building the model. It's basically split the data into training and testing, then build the model using the training data set, evaluate the data using the different evaluations that I showed you last session, using the R square, using the correlation coefficient, absolute error, percent factor, and so on. Once the model is good, now you can use it to predict any well or liquid rate in the future. So for the data, this is the data that I had in this project here. We have gas oil ratio, upstream pressure, downstream pressure, the choke size, and water cut. We had here oil, gas, and water production, and we had the oil production. So what happened here? We collected so many samples, we collected so many data points here based on a separator test. Test separator, we have here test separator like around 1500 point, and each one we know what is the water cut, the choke size at that time, the downstream pressure, upstream pressure, and the gas oil ratio. For the data analysis here, this is the univariate analysis. We know what is the mean, where is the mean for each parameter, the standard deviation, the minimum, the quartiles, the maximum, and the skewness factor in order to see the uniformity or the distribution of the parameters. As you can see here, from this one here, most of the parameter has almost a good normal distribution, except the water cut and the gas oil ratio, which is a little bit skewed to the right, to the left. So another one, which is the visualization for this one here, the scattered plot. You can see here all the parameter versus each other. So it's basically the gas oil ratio for the first one here versus the flow rate, and then versus the water cut versus the choke size versus the downstream and the upstream pressure, and so on. And this one here in the diagonal here show you the distribution of the data point. It's clearly that also proof from the previous table that most of the parameter has a good distribution, except for the gas oil ratio here. It's a little bit, most of the data here was going toward or concentrated towards the lower end of the gas oil ratio, but we still have some data point up to 10,000 standard cubic feet per stock tank barrel. For the water cut, similarly, we have too many data points at zero water cut, where we don't have a water production, and some of the data point with water production. If you look from this one here, it also gives you the distribution, the scale for each one. So the gas here would vary from, let's say, 100 standard cubic feet to 10,000 standard cubic feet. Upstream and downstream pressure would vary from around 400 psi to 2000 psi. The choke size also vary from around 10 to 150. The water cut from 0 to 40%, and the oil rate vary from 1,000 to around 9,000 stock tank barrel. So this one here gave us the first thing is the distribution for each parameter plus the scale. We know the scale for each one, and from it also we can see if there is a good relationship between the oil rate, which is this one here, and the other parameter. So it is clearly that from here the choke size here has the highest correlation with the oil flow rate. So you can see here it's we almost have a certain trend here, but the rest of the parameter does not show any relationship. So when we did the correlation coefficient heat map, you can see here the water cut, it has a correlation coefficient of 0.21 with the actual flow rate. The choke size has around 0.85 correlation coefficient with the oil rate. The downstream pressure is almost zero, almost has no effect on the flow rate. The upstream is 0.24. The gas oil ratio is 0.3%. So now what we're gonna need to do is to do some transformation, some scaling for the data, and maybe some classification for the data itself, categorizing the data, categorizing the problem. So the first thing I did here is data transformation. What I did, I convert the gas oil ratio to log. Instead of using gas oil ratio, I used log gas oil ratio. So the gas oil ratio now, log gas oil ratio is vary from the 3 to 4. And then I did scaling for most of the parameters in order to have almost the same order. So it's vary from 0 to 1 for most of them. And in this one here, what I use here, the normalization technique, which is basically x, x minus x minimum divided by x maximum minus x minimum. Okay, so this one here gave me the range for all the parameters between 0 and 1. And for the gas oil ratio here, it's almost from 3 to 4. So it's still in the same order. And I can also make a scaling for this one here to be from 0 to 1. After the transformation, you can see here that the correlation coefficient a little bit increased. In case of gas oil ratio from 0.3, it increased to 0.36. But for the rest of the parameter, as there was no any transformation, just normalization, the correlation coefficient did not change. The next step, what I did here is, so this one here is basically comparing the correlation coefficient. This one here was 0.36 before the transformation, and after the transformation, it increased the correlation coefficient to 0.36. That means our transformation improved the dependency of the flow rate in the on the gas oil ratio parameter. And from the physics, we know that from the physics of the multiphase flow or the flow through the choke, we know that the flow can be classified into two categories based on the flow phenomena into critical flow and subcritical flow. Where the critical flow, we have the downstream pressure to the upstream pressure is less than 0.55. Sometimes some other reference can say 0.5. And the subcritical, where the downstream to the upstream pressure is higher than, so sorry, this one here is higher than the 0.55. So in this condition here, we can classify our data point into critical and in subcritical. And from the physics also, we know that in case of the critical, the upstream pressure here is controlling the flow rate, and the downstream pressure has no effect on the behavior or the flow rate of the well. In case of subcritical flow, the flow rate is a function of the downstream and the upstream pressure together. So what we did here, we classify the data, we divided the data into two categories. The first one, so the first one here is the subcritical here. So this one here, when we classify, we only took the data set, which is higher with downstream to upstream pressure higher than 0.55, and we name it, this is the subcritical category or class. You can see here, your correlation coefficient slightly increased in some parameters and then other decreased. So for the water cut, for example, increased from 0.21 to 0.3. Okay, the choke size is from 0.85 to 0.8. So now the flow rate is not just depend on the choke size, which is comparing to original data set. It's basically this one here is very high and the rest was very small. So now by doing this classification here, we distributed the importance of these parameters. Okay, see here the upstream is 0.33 comparing to 0.24, and the downstream pressure is 0.3 now instead of almost 0. So with the classification, the first class here, we were able to improve the correlation coefficient between the input parameter or the input features and the output. See here also, this one here for the critical flow, the second class. Second class, when I'm comparing the correlation coefficient of the parameters with the oil rate, you can see that gas oil ratio here increased, the choke size 0.91, more increase, more dependency, the upstream 0.37, and the water cut 0.19. So this one here show very good improvement, high improvement in the correlation coefficient between the features and the output. So this class here was good enough in order, especially in case of the critical one. Regarding the subcritical, so this is the subcritical, and this is the data distribution. We still have one issue here, which is the water cut. The water cut, most of the data point here was almost zero, and we still have some which is not zero. That means we can classify the data into two classes, one with water production and one without water production. So now, based on this classification, we divided our data into three categories. The first one, so we have all data here. We classified to critical data or critical data point where the upstream pressure, the downstream pressure over the upstream pressure is less than 0.55, and then the other one is subcritical. And for the subcritical here, I divided or classify it into with a water cut equal to 0 and another one with water cut up greater than 0. So now we divided our problem from one problem into three different problems here, and now we can solve each one by itself. So for the model development, this one here, if we use the whole data, as it is without classification, we were able to find this is the training and this is the testing. The R square for this one here is 0.94. The R value, correlation coefficient, is 0.97. The ABE is 10%, and the MSE is 0.003. This is still very good match, actually. But when you look to the testing data set, the error increased to 15%, and your R square is become below than 90%. Even if you don't have anything to work with, this one here is still a good match between the actual and the predicted one. But is the classification gonna improve this behavior? Let's see. So for the first class, which is the critical flow, for the critical flow data set, where your data, the downstream pressure over the upstream pressure is less than 0.55, and your flow rate is not a function of the downstream pressure anymore, only a function of the choke size, upstream pressure, gas oil ratio, and the water cut. So you can see here a huge improvement in the model behavior. So this one here cross plot, so this cross plot here between the actual and the predicted one, your data is almost aligned to the 45-degree. Most of the data is around this one here. That's mean at 0.4, for example, you will able to see that your predicted value is 0.4. If you look to the R square, the correlation coefficient is almost close to 1. Error here is 4, and the MSE is 0.001 or 0.001. For the testing, we have a good testing results with R square of 0.92, correlation coefficient 0.96, the error is 10, and the MSE is 0.03. So now the first class showed us that by classifying our problem and dividing our problem from dividing the whole data set into subsets, which is the first one, the critical, we are able to improve the model behavior. So at the beginning, see most of the data was scattered. If this one here is your 45-degree line, you see that some data point here is completely scattered away from the 45-degree line. And if you look to the data set here, the testing data set, you have the error here is very high. But when we classify this one here into the critical data set, for the training and testing, we had a good results. Another one for the evaluation is the trend, to see the trend. So this one here show the oil rate was for a different data points. So this is the data index versus the oil rate. The red one here It's basic is the actual flow rate, and the blue is the model prediction. So in this one here, in the one here in the top here, I use the random forest. We use the random forest in order to predict the flow rate as a function of the input parameter. And this is very good match between the actual and the predicted data set. Similarly, for the second one here, where we used the support vector machine, another machine learning technique. Also, we had a good match between the actual and the predicted flow rate. So now that's proof that our model can be used to predict the oil flow rate if we are above the critical condition or the critical criteria. What about the subcritical one? For the subcritical flow, you can see, so this is subcritical flow. In this one here, this is all the subcritical data. If you look to the 45-degree, yes, your data point is around the 45, but with some scattering around, it's far from the 45. The R square is 0.88, R is 0.93, and the error is 14 or 15%. For the test data set, you can see here that your R square is very low, 0.85, and the R is 0.92, with the error of 16.5. After we classify this one here, so we set the subcritical, we will classify it into with water or without water. So without water, this was the results. Without water, as water cut equal to 0, the results here is very good. You can see that all the data here is aligned with the 45-degree line. The error is become 4, R square is 0.98, and the R is 0.99. Similarly, for the testing, the R square is 0.9, R is 0.95, and the error is 10 with MSE of 0.005. So now when we classify the subcritical to a water cut equal to 0, see this one here jump from R square of 0.88 to almost 0.99. For the second part, which is the subcritical here with water cut, in this one here greater than 0, we have a water production in this one here. Also, we have very good results, okay, for the prediction of the flow rate as a function of the input parameters. Another validation or verification for this one here is the trend. If you look to the trend, of this one here for the subcritical with a water cut equal to 0, very good R square between the actual and the predicted with using the AMPHIS model here. So in this one here, one of the AI technique, which is AMPHIS, you can see here that your data also in a very good match between the actual and the predicted one. So that means now this one here can be used to predict the oil flow rate when the fluid flow under subcritical condition with water cut equal to 0. So that means there is no water production in this one here. For the second one, which is the water cut greater than 0, this is the model results. And then in order to show that you did a very great job in your work, it will be better if you can show comparison between your results and the literature. So as I said before, for the model evaluation part, how can we judge that this correlation coefficient or this R square is good enough or not? So as I said before, it depends on what you have in your hand. So if in the literature, there is no way to predict the oil flow rate from the input parameter, which is the choke parameter here, okay? If you can get any equation or any methods that can predict this one here with a 70% accuracy, that's very good, because before that we don't have anything in our hand in order to calculate the flow rate. But if there is some correlation that can be used to calculate this one, the oil flow rate from the production, from the choke parameter, that means you need to have a model that has high accuracy comparing to the literature. So in this one here, as I said in the introduction section, there is many correlations that were developed in order to predict the oil rate from the choke. So it is important to show a comparison and show how is your model behavior comparing to the correlation. Or if there is some AI technique that already developed for this problem here, you need also to show how your model is better than the other. Other than that, you are doing nothing. You are adding nothing to the literature. So for this one here, a comparison between the model that developed for this one here using the machine learning versus other correlations here from like Gilbert until the last one in 2019. The AABE is very small comparing to the other technique here. And if you look to the R square, it's 0.98 with a correlation coefficient 0.98 also, or 0.99. Comparing to the other one here, it's almost 0.7. The highest one was 0.7. So that's give us an idea that using the AI has a great job in order to improve, in order to predict the oil flow rate from the choke parameter. Okay, so this was the first one here. This was the first one in order to predict the application of AI in production, in the application of AI in the production engineering, which is the prediction of oil flow rate from the choke parameter. The second example that I have here is application of the AI in a well logging or drilling application. Sorry, I have something. So the second one here is the application of somehow. Give me a minute, please. Yeah, here it is. So the second example is application of well logging and drilling application. So we have like in the too many data that we can collect from the drilling. During the drilling, you have so many data. You are measuring this one here automatically at rig using the weight on bed, the mud density, the rate of penetration, and so on. So one application of the AI is to estimate the well logs from this drilling parameter, because the drilling parameter here is sensitive to the formation. It's a function of the formation properties. So why not we can use this one here in order to estimate one of the gamma ray. So the first one here that we used the AI in order to do so is gamma ray prediction. We want to predict the gamma ray from the drilling parameter. So gamma ray here is very important parameter in order to classify the lithology of the formation, in order to identify the presence of clay content or not in the formation. And this gamma ray here is usually can be measured through the core analysis or using the LWD logging while drilling. So basically we can have a tool, the logging tool behind the drill bit, and this tool here can be used to measure the gamma ray inside the formation. The problem with this two method here is high cost, in order to retrieve the cores from the formation and take it to the lab doing your petrophysical analysis in order to calculate the gamma ray. This is very cost and time consuming method. The second one here, LWD, this is very expensive tool, very expensive process. Plus, when you are drilling, usually your logging while drilling tools is behind like few hundred feet from the drill bit. So that means when you are drilling, the formation that you are drilling on, you are not measuring the gamma ray on this one here. which may have some issues related to the wellbore stability. You don't know if you have here clay, you're gonna have some wellbore instability in this one here during the drilling, because you don't know instantaneously gamma ray or a clay content measurement. And this was here our objective is to estimate the gamma ray using the available data in order to, which is the drilling parameter. This drilling parameter include, like as I said before, weight on bed, the torque, rate of penetration, the horsepower, which includes the pressure and the flow rate. So the first thing here is our data. The data here, we have the flow rate. We have around 4,600 point. And the mean for this one here, for each one, we have the mean, standard deviation, minimum, maximum, also the uniform, the distribution parameters here, and the correlation coefficient with the gamma ray. So this one here, it can show, you can see that there is some correlation between the drilling parameter and the gamma ray. And in this one here, the gamma ray was vary from around 28 ABI up to 300 ABI. As a result, I used here the log gamma ray in order to transform the data from the log distribution, log normal distribution into normal distribution. So you can see here now the minimum for the gamma ray is 0.8, maximum is 2.8, and I did the same for all the parameter here. We did some normalization in order to have it between 0 and 1 in order to have a good effect on the gamma ray instead of not just the scale. So this one here shows the data distribution of your data. This one here, the log gamma ray here, show very good distribution, almost normal distribution, and the rest of your data almost have a fair distribution. I have here 3 curves here. The green one here was for the training, the blue one for the testing, and the orange one for the validation. So as I have here a good set of data, I have around 4,600 point. So I was able to split this one here. So this one here was basically around 3 wells. So I used 2 wells in order to build the model and 1 well to validate the model. So the 2 wells here, I used it for the development. Development include training and testing, and the third one for the validation. In the third one, it is basically unseen data for the model. So the model was never saw the validation data point before while the developing. That's to make sure that the model after the development can be able to predict the data, can be able to predict the gamma ray for any other data point. So you can see here also one of the issues or the problems that can face you in the development is the representation of the data set, which is one of the problem I showed you also last session, which is the data representation, data set representation. If the data set is not representative for the other data point, it may give you a huge error. Sometimes your training is high and your testing or validation, the error is low, or other way around. That means you need to make sure that your data points that you are using in the training and the testing and the validation are representative to the formation. So it is in the same range. This is what's important for us. So if you came with a data point which is above this one here or lower than the rate of penetration, this may give you an error in the estimation. After building the model, we split the data point into training testing for the 2 wells. Then we developed the model, build the model, change the model parameters in order to have a better value for the R square, R, and so on. After that, we use the model to validate the unseen, to be validated using the unseen data. So we predicted the gamma ray for the third well without using the drilling parameters. If we saw the results here, so this results here shows the measured gamma ray versus the predicted gamma ray in a log API. As you can see here, very good results between the actual and the predicted gamma ray. So this one here is a training data set. The correlation coefficient was 0.93 and the error was 3.8%. Then for the testing data set, almost similar results here. The CC correlation coefficient 0.94, and the error is 4 also. And then for the validation with the unseen data here, almost have the same results here. The error is 4, the correlation coefficient is 0.96. That means that your model here is very good and it's ready to be used in the future to predict any data as far as this data here has input within the range of the model input data. Another way of evaluating of checking the validity of your data here is the trend. So this one here is the gamma ray with the depths, and instead of the depths here I'm using here the index, but it is referring to the depths of the formation here. You can see here this one here for the training data set. The results here is very good. You can see that the actual one in blue and the predicted one in green is almost match with correlation coefficient 0.96, AABE is 4%. Similarly for the other two curves here, except we have here some mismatching between the model and the between the model and the predicted and the actual gamma ray here. But other than that, the model was able to track most of the trend for this one here. So if it's increased, it increased with it. If it decreased, it decreased with it. That means this model here can give you a continuous profile because your data is a continuous profile. The drilling data is continuous profile with each feet, with depths. At each depth here, you can have weight on bed, rate of penetration, density of the fluid, and so on. So this one here can be translated into gamma ray log. So it gives you a continuous profile for the well log instead of using the course, and the course can be from one depth and another and so on. So which is not continuous profile. So this is also one of the advantage for using the AI in order to predict the gamma ray logs. Another evaluation for the regression or for the AI machine is the residual comparison. So if you estimate the residual, and if you remember from last time, the residual is basically the actual gamma ray minus the gamma ray predicted. So this one here is the actual versus the predicted gamma ray without any absolute. That means this one here, it may be negative or positive, depends on which one is higher and which one is lower. In order to make sure that your regression or your AI evaluation or building was good, this one here has to have almost a normal distribution. The error here has to have a normal distribution with a mean of almost 0. Okay, so your residual, in order to confirm that your development is good, your error should be something like that. This is the 0, and it almost have a normal distribution with a mean of 0. The data point here with a negative residual should be almost similar to the data point with a positive residual. You can see that, yes, almost with a 3 different technique here. We use ANN, AMPHIS, and function network. Most of them almost show a normal uniform distribution for the error and almost localized at the 0 point. That means that the model was able to match and was able to have a similar weight for all the gamma ray range. Okay, so this was the second example of building AI technique in order to estimate one of the well logs from a drilling parameter. This can be applied to any other logs that you see that this one here can be related to the formation. So as I said, the drilling parameters, weight on bit, rate of penetration, torque, all these parameters here is related to the formation. If the formation is hard, it will be difficult to be drilled. So this one here also can be related to any of other logs. For example, the sonic, okay, sonic logs or porosity. You can estimate the porosity from this one here. If you have a log neutron porosity, for example, you can estimate it also from the drilling parameter, because also this porosity here is related to the formation. So this one here also. So another ideas for using the drilling parameter is to estimate many logs of formats. The porosity is related to the formation, gamma ray related to the mineralogy, delta sonic also the shear or the compression velocity or the shear velocity. It is related to the compaction of the formation, which is also related to the cuttability or the breakability of the formation, which also in another way is related to the drilling ability. So using this technique here, this is just an idea. You can use it to predict as many as parameter using the available data from the drilling. The third example that I have here is related a little bit to the reservoir engineering. So for reservoir engineering application, you can there is two categories of AI application. The first category is the categorization. The second category is production analysis. For the categorization, this include the prediction of reservoir flow property, for example, the Z factor from certain gas composition, or prediction of the oil formation volume factor, similar to the example that I gave to you during the first session. So your oil formation volume factor can be estimated. So there is, instead of doing BVT analysis in order to have this one here, it's very expensive in order to take the samples. So this all of it is issue. So if you can build AI models that can predict the oil formation volume factor from, like for example, the pressure of the formation, the temperature, maybe the composition or a gas-oil ratio, the API of the fluid, liquid gravity. So this one here also can be used. So this is basically characterization. You can characterize your formation or the property. You have only one parameter here. Or you can get a porosity, for example, from the well logging, or permeability from the well logging, and so on. So this one here, all of it, it's just characterization. The second one is production analysis. So on the production analysis, I don't have example for it here, but it's basically in order to have a recovery, you need your reservoir. Okay, so you have a reservoir here, and then you have your compilation, whatever the compilation is, and this will be your recovery. So the recovery here is a function of the compilation, design, and your reservoir. So one way for the application of AI and reservoir engineering is the history matching. History matching, you don't know what is the reservoir properties, what is the porosity, what is the relative permeability, what is the absorption parameters, and you can use whatever is the recovery is, and you can use the current compilation, and you can try to use the AI in order to predict the parameters of the reservoir. Another application of it is to optimize the compilation here using the AI. So you build the relationship between the recovery, compilation for a certain reservoir, and then you can use this relationship to optimize this one here in order to optimize or increase the recovery. For today's example, inshallah, I can just one of the characterization, which is the total organic carbon content. So for the total organic carbon content is very important for the unconventional reservoir, especially shale. So TOC is very important. It can give us an idea about the maturity of the formation, if this one here is good enough as a source for the hydrocarbon or not. The TOC, it's usually can be measured experimentally using core samples from the formation and then take it to the lab and then do some experimental in order to have this one here. This one here is very difficult, time consuming, and the cost is very high. Plus, it will also give you just a scattered point. So for the whole well, you will able to take sample here, core sample here, core sample here, and another one here. So you have only 2OC concentration at this point only. There is some empirical correlation similar to the one that I showed you also on the oil rate prediction. There is some correlation as a function of the logging, but this one here was localized with some uncertainty. So this gave us the objective for us here is to predict the TOC using the AI technique. So the data that we used in this one here is well logging data. So we basically have different well logging here, including the formation resistivity, spontaneous potential, sonic transit time, bulk density, neutron porosity, gamma ray, spectrum logs, and so on, calcium, uranium, and the TOC here based on a log analysis. So the data points that we have here is basically at a certain depth, we had this logs, and we had measurement from the lab in order to estimate the TOC. Then we use this one here to build our model, and this is short for the model process. We basically collect the data with some statistical analysis to see the scale of each parameter, do some transformation for the logs. So usually the gamma ray, usually some of this one here was like the minimum is here, the maximum is here. That means the scale for this one here, the range for this one here is very high compared to the density, for example. That means you need to do some scaling transformation. The uranium weight percent is 1 to 22. The porosity is very small from 0.01 to 0.3. So this scale difference here can give you a huge effect on the performance of the model. So it's very important to have a conversion, have data transformation for this one here. For example, I used log the resistivity in order to convert the data to be in range from 3 to 4 or 3 to 5. And similarly, the other one here, the delta T, you used here a square root. The other one, I just use data normalization. So this is the statistical analysis. And then the second step is randomly split the data into testing and training using 70-30. Then select the model parameter using for any model. For example, if you're going to use A and N, there is different hyperparameters that you can use to optimize the model, number of hidden layer, number of neurons, and so on, the learning rate. Random forest, there is number of decision tree, and so on. Run the model in order to train the model, calculate or evaluate the model using the correlation coefficient, the error, and check, is this one here is good enough or not? If it's good, that means you can go ahead and test your model with the validation data set in order to make sure that your model is working well. If not, you need to update the AI code, update the AI parameters, okay? Or sometimes you're gonna need to change the splitting ratio. So this is the developed model, the chart that we use on this one here, and it is similar to any other problem. You can use it for any other problem. Start with data gathering, analysis for the data, then splitting the data, developing the model using the training data set, and then test the model using the testing data set. This is the results for the model. Very nice results between the prediction and the actual data set. With our correlation coefficient is almost 0.99. For the testing is 0.93, which is fair, very or a good results between the actual and predicted one. So to summarize, to conclude, for the AI, application in petroleum industry or any other industry. It depends on your understanding for your data. So your data need to clean, make some analysis on this data, univariate analysis in order to know the scale, to see the scale of each parameter. You may need to convert or to transform this data or make a normalization, standardization, then see the relationship between the input and the output, between the TUC, for example, and the other input, which one has a high correlation coefficient, how to improve the correlation coefficient by making some transformation, and then split the data to testing and training. And it will be optimum if you have another data set here, which is a validation data set, which is unseen to the model. So it is not even here during the splitting. So this one here will be an optimum. But if your data set is limited, you can have it as a training and testing. And this one here should give you a fair results. Use a training data set in order to develop the model. You're gonna need to change some of the model parameters in order to have a better training. Test your data or evaluate your model using the evaluation, the cross plot, the trend, the R square, R, the error, and so on. Once you are satisfied with the results, you can use the model to test and validate more data. So this is one here can be applied to many application, production, reservoir drilling, but you need to know your problem first. As you saw in the first example, in the oil flow rate, based on the physics, I did know that the flow rate can be classified into critical and subcritical. And this helped me a lot in order to increase the correlation coefficient. So know your problem, make analysis for your data, and it will be easy to build your model. So this is what I have for today. That's it, and I will be happy, inshallah, to answer your questions.
Thank you, Dr. Ibrahim, for the time you dedicated to deliver this series of lecture. We highly appreciate that, and we are looking forward to having you in future webinars and events. And I hope that all attendees by now have a clearer understanding of the applications of artificial intelligence in the petroleum industry. So I want to remind you of some ground rules to be able to receive a certificate for this course. And I'm sure that by now most of you know. So first, you have to complete the assigned quizzes on Google Classroom with a passing grade of 70%. And second, you should check Arab Guru's Facebook group and the Google Classroom for the final exam date. And note that you can't miss the final exam, and the passing grade is also 70%. So that's all for today. I want to wish you best of luck and have a nice day.
Thank you.